Correlation and regression are very different processes. So what I'm going to talk about today is regression. So correlation tells you if two things are associated with each other and if there's potentially some causation between them. What regression does is it actually builds a predictive model where you can use values of the variable on the x-axis to predict values along the y-axis. So simple linear regression such as this, I've got height and weight, I've got men and women with different colours and shapes, and it shows that as your height increases, so does your weight, because roughly you're kind of like a cylinder. So this is the first thing you need to think about before you do any of the calculations in a regression. You need to plot the scatter plot. If the plot is linear, and if the data points are spread over a range of x and they're evenly spread in x with no breaks, and there's an obvious slope to the data, then you can go on and do regression. If the answer to any of these questions is no, then you need to think about what you need to do. So for example, if you've got gaps, then improve the collection of data to fill in the gaps. Make sure that your sampling is as effective as it can be. If it's not linear, then think about transforming one of the variables to get a linear relationship. You've seen this already in Lineweaver-Burke plots, which transform a very non-linear Michaelis-Menten plot into a straight line. If there's no slope, or if it looks like it's horizontal, then there's probably no correlation and regression's not going to work. Now, regression works on a linear model idea. So linear models are the ones that we prefer to work with. Non-linear models are somewhat challenging. So a linear model is based on the basic equation for a straight line, so y equals mx plus c. So y equals a plus bx. It doesn't matter how you formulate it, but y equals something multiplied by the values of x plus some kind of constant. So the something that's multiplying each value of x means as x changes by 1, y changes by that constant. So that is the gradient. Now the best model through a set of data will be that has the best agreement with the data points and where the line fitted minimises how far those points lie off that line. Now that can be done with a process called least squared fitting. This was devised by Gauss, and he actually used this as a method for finding the Gaussian distribution, and it is exact. It works exactly, and it will find you a unique line through a set of data. You just run the equation and you end up with a line. It's not like sliding your ruler through the data and trying various different slopes and lines. There is one solution. So what it does is it minimises the difference between the y of the line and the y of each of the actual points, and it keeps minimizing those errors until you get your unique fit. So you can calculate the sum of x, the sum of x squared, the sum of the squares of x, the sum of y, and the sum of xy. So you can figure out the slope, which is b, equals n sum of xy minus the sum of x times the sum of y divided by n times the sum of the squares of x minus the sum of x squared. Once you've figured out the slope, then you can put that into the equation of the straight line. So y equals mx plus c, or y equals a plus bx. What you do is put in the gradient, you then put in the mean value of y and the mean value of x, and from this you can figure out the constant. So for example, using the data that we had for the chickens and their eggs from the correlation data from Spearman and Pearson's, b equals 13 times 661 minus 161.2 times 47.3 over 30. Anyway, it ends up being 0.4805. And a, when you substitute in the mean value of y and the mean value of x, turns out to be minus 2.31994. So that is the intercept. You're familiar with doing regression in Excel. You put in your data, your x and y data, you do the scatter plot, and you ask Excel to add a line. So this is the line added by Excel. So you can see y equals 0.4805x, which is exactly what we found by doing it by hand, minus 2.139. So the intercept is minus 2.3199. That's the value of y when x equals 0. And the r squared is 0.9873, which is the square of the Pearson's correlation, the r of 0.99 that we found in the correlation exercise. So this is something that Excel does well, fitting the line and giving you a nice, easy demonstration of the correlation and the linear regression model. There's nothing wrong with this. What it's missing is the diagnostics. And the main problem with any linear regression is knowing, is that actually the best regression line? In this case, there's probably no issues because there's such a strong relationship between the two. It's very difficult to mess up fitting the model, but that's not always the case.